Our group consists of Hao, Wenhan, and Lin Xiao, and the topic today is about a deep learning technique for undersampled MRI reconstruction. We would like to thank Proof Liu and Proof McFin for listening to this recording and evaluating our work. First, we will talk about our implementation of the sense reconstruction. Then we will show how deep learning can refine the artifacts if the case space from each coil was even further undersampled in what we call aggressive undersampling. Firstly, case space undersampling sense reconstruction. As we all know, MRI can suffer from a very long scanning time to acquire fully case-based data. Therefore, undersampled reconstruction techniques were developed. In this project, we will mainly consider aliasing. The binary mask shown here has alternating rows of 0 seconds and 1 second, which will lead to aliasing as observed in the aliasing image here. One of the methods to solve aliasing in the sense reconstruction method, which we have re-implemented ourselves in Python. Here, the first row in the case-based data of each coil after undersampling. As you can see, the result image for each coil seems to have the object repeat itself, which is aliasing. If we do a new sum of square reconstruction, the resulting image will repeat itself too. However, if we do the same reconstruction, the problem will be solved. The problem with the same reconstruction is that each coil still requires a lot of case-based data. Therefore, we wonder what happens if we undersample each coil even more. In what we call aggressive undersampling, we will consider two methods. First and foremost, the reconstruction undersampling. As you can see, the ideal binary mask in the middle mostly sampled the low frequency region. There are two consequences. Firstly, without high frequencies, the image will lose a lot of details and sharpness. Secondly, since the filter is ideal, it will lead to gibbous ringing artifacts, which will still be there after sense reconstruction. We will use deep learning to see if we can eliminate those artifacts.
Okay, then we consider aliasing and ringing at the same time. The binary mask in the middle samples the low frequency region moderately, and the high frequency region was sampled too, but only randomly with some random interval. The purpose is to see if our deep learning method can remove moderate aliasing artifacts also. As you might expect, aliasing artifacts are prevalent in the left image. This slide shows the effects of aggressive undersampling on sense reconstruction. As you can see, the ringing and the aliasing artifacts are still there. Now, our interest is how we can fix these artifacts. One solution is artifacts removal on the sense reconstruction with deep learning. Supervised approach can be inefficient because of the need for labeled datasets. In this project, we leverage the deep image PRIO technology, which is self-supervised and does not require labeled data. The only information available is the bad sense reconstruction. If we are supervised learning, we are hoping for the aggressively undersampled sense reconstruction yi to return to the normally undersampled sense reconstruction xi. Here, we need to find the theta such that the loss function between the inverse operation of yi and xi is minimized. However, this is problematic because we did not have the information about xi. The objective of self-supervised learning is to find the theta that minimizes the loss between yi and the forward operation of the inverse operation of yi. We wish to find the interval operation I so that we can have the normally undersampled version. Finding I is not trivial, and there has been many methods proposed, and it turns out that we can approximate I by using a deep neural network.
So However, as we have established before, we don't have any ground truth for xi, which typically acts as priors for the deep learning model. So the question is, what kind of priors can the inverse operation I theta has? And there's a work in the CVPR conferences have shown that the structure of the generated network is enough to capture radio of low-level image details before any learning. Or in other words, the model architecture is a prior in itself. So this is how the method works. Firstly, we input a random noise and we will do a forward operation on the noise. And then we will try to minimize the loss between the corrupted image and the noise. And so after so many iterations, the image will slowly be reconstructed. And before the model overfits, at some point, the output will be a very clean looking image. So this is some examples of the deep image prior technique. We're mostly concerned with the noising application here, where you can see that there are a lot of noises in the corrupted image, but it has been corrected thanks to the image prior technique. So this is related to our task at hand, because we can consider the GIFs and the aliasing artifacts as noises, and we will see that if the image prior can be applied the same way to remove those artifacts. So this is a rough pseudo code. First, we will generate some noises, and we will do a forward operation on the noises, and we'll get the output. And then we will try to minimize the loss between the output and I hat, which is the corrupted image. So here are the results of the deep sense results. As you can see, here there's a lot of ring gain artifacts in both the brain regions and the eye regions. But thanks to the deep sense method, it has those artifacts have been reduced. And we report a similar, and we will evaluate the methods based on the structure similarity and the peak signal to noise ratio index. As you can see that the structure similarity is roughly the same, and the peak signal to noise ratio for the deep sense method has increased. A similar result, a similar effect can be observed in the deep sense results for method 2, which has aliasing. As you can see in the backset reconstruction here, there are a lot of artifacts of aliasing, but these have been completely removed thanks to deep learning. And we have reported an increase in both the structure similarity and the peak signal to noise ratio. So in summary, what we have done in this project is we implemented ourselves the sense recursion algorithm and the deep image prior technique. We can see that if we combine those two techniques, we can correct aggressively in the sample sense reconstruction. And as aggressive in the sample, as we have shown that it means to further undersample the case space data for each coil. And we can do this without any ground truth label. So we can think of this as an Bayesian approach where we use the model structure as the prior. So one of the proposals is semi-supervised deep image prior. So as seen, we did not use any ground truth label. So the natural question is to ask, will adding some label data enhance performance? So this is the end of our presentation. Thank you, professors, so much for taking your time to listen.